Consider this conjunction. That is to say, statement need to be proven. If we succeed, then it becomes a theorem. So what it says, if we take any integer, x and y, and we find their sum and their product, okay, and we find them to be even, then both x and y are even. All right, so we're gonna write this one in more precise way so we can see the structure. For that reason, I'm gonna be using the predicate e of x to mean x is even. Also, I'm gonna use O of x to mean x is odd. All right, so let's do it now. So in the translation, we also need to look for the connector. So we see here f, we see here and, we see here another and. All right, let's do that then. So we have here the implication, and then we have x times y and even, and the sum is even, so that's what it really mean. Okay, and on the other side here we have x is even and y is even. All right, so if we were to go ahead and prove this, we need to assume this, and we need to show that we arrive to that. It turns out it's really easy to start the other way around. So what that means, we need to get the contraposition for this one. So if you recall the contraposition of something like that, if P then Q, we know this is the same as saying if not Q, then not P. All right, so this is just a note for ourselves to remember. So we're gonna do that. So we're gonna bring this one over here. So we'll be, but with negation. All right, so gonna be not even and y is even is imply. All right, I'm gonna bring this over here, the product and the sum, x plus y. Okay. All right, so then we're gonna also benefit from some other rule we learned throughout the course, and that is a rule that says if you have something like this, P and Q, that allow how to distribute the negation. This is the De Morgan. This is the same as not P or not Q. So we're gonna use it on both sides. So, but I'm gonna go do it quicker. So instead of when not even, I'm gonna just say odd. So here will be odd x, and this one will be or, and the odd y. All right, imply. They're going to do the same thing, so this one will become or, and this from odd going to be even. Okay, and the same thing here. All right, that is simpler. Okay, now we have something clear. So in order to prove this, I need to assume this side, and then I have to show this one to follow. But we notice that this involves the or. So we recall that when we have something like that, I need to use proof by cases. Let me just remind us what that means. So if I have something like this, P or Q, if I want to show that W follow, I need to assume P. So remember, we use something like that, and then somehow I need to arrive at W. Also, I need to assume, I'm putting this between round square to indicate that is assumption. I have to assume Q. I need to arrive at W. If I do this, then I just proven W. So what that mean? This one is mean that if P or Q then W. And this is how we prove it. I need to show it. So let's apply it here. So I need to assume this part. I have to arrive at this one. This only will be our W. And I have to assume this and then arrive at W at the same time. Okay, so let's do it. All right, so based on the discussion that we had before, we're going to have something like that. And so we need to assume that X or Y are odd. So recall from the truth table for the OR. So when this one is true, when both, when or either. So in this situation. So we need to consider when both are odd, when either one is odd and the other one is even. But the when both of them are even, that is not considered. Okay, so we need to consider all these cases. Now, we are faced with a situation where there is a potential for repetition. So notice, if you look at the X, or the possibility under X, we have odd, odd, even, and also under the Y, odd, odd, or even. All this is the same problem. So this is why we without repeating ourselves, we say, you know what, what to choose. Either choose X to be odd, and then I keep switching the Y between odd and even, or I could choose the Y. This is really arbitrary choice. So in this example, all right, after we decide the contraposition and we have it in this format, I'm going to say, I'm going to go ahead and assume X is odd. What that means, I'm going to fix X to be odd, and then I'm going to change, I'm going to consider the case where Y is odd and Y is even. And when I do that, and I'm done really. Okay, so this is the first case. So I'm here, I'm assume that X is odd. Okay, and because it's odd, then it is equal to times m plus 1. So remember what the definition of odd of even. So something, okay, let me just write it to remember. If I say something A is even, what that means, there is the K, the 2K, where K is integer. If it is odd, let's say B is odd, then I say 2K plus 1. What's the important, this one is some integer. So for this reason, because we assume X to be odd, then it's 2m plus 1, where m is an integer. Okay. Then what I'm going to do here, what you can see, I'm going to consider the cases where one time when Y is even, which is this case, and then I'm going to consider the case when Y is odd, which is the top case. So, all right, now this way I'm covering all possible cases. Now, I'm gonna say without loss of generality. What that means, I'm gonna assume X. But I could have said Y is odd. There's no difference. So exactly the same proof. So that I'm going to do it only one time. I don't have to repeat myself. That's the whole point of this statement, without loss of generality. Okay? Just you can assume either one. Anyway, so now we have Y is even. And because even, then is equal to 2 times n, where n is some integer. Now when we add X and Y, okay, so remember X equal to 2m plus 1 and Y equal to 2n, just 2n. When I add them, so I have X plus Y is equal to this side. You have to 2m plus 1 plus 2n. Okay, this one here. So you can see it here. I just here so want to show, but it is here. All right. So what I have here, this is the X, this is the Y, and then I factor out 2, and what I get 2 times this number. What this number? This is integer. Integer plus integer is integer. Okay, I could have called it R, for example. So what that mean? It means the sum is odd. Okay, that's enough. And notice here the consequent. I need just to show one of these. Okay, so here I succeeded with that. Now we're gonna assume y is odd, but as you notice, x is still fixed to be odd. So if y is odd, then gonna be written as y2n plus 1. So when I do the multiplication, you know, I could choose the multiplication or the addition. So in the proof here, we choose the addition. I could have chosen the multiplication or the same. I could have choose the my choice here, this one or this. Why? Because the consequent, it's this the product or the sum. So you can choose either one. In case you are wondering why we didn't do the x the addition, so it doesn't really matter. But you know, just to get the flavor of having both. So this is x. This whole thing is x. And this whole thing is y. When I multiply, I get this. So what this whole thing here, this whole thing is integer. Why? Because anything times integer is integer. When I add integer, I get back integer. So I get 2 times integer plus 1. What that means? That is just odd. The definition of odd, like we have it here. So we said this complete the proof because the other way around is to say, to start from the y, to fix the y, and keep changing the x's. But this whole thing is really similar. Recall the rule of existence, existential generalization. So what that means, if I can find something, then I can just generalize. So for example, if I know someone, I know some person, okay, I know some person, say some individual A, I know that A is tall, right? If I'm gonna write it a P of A, I know some guy, A is tall. Then I guess they can go ahead, therefore, there exists some X such that P of X. This is again, it's his statement. What Siri said is say there are at least one person, there are some person that are tall, at least one. Okay, it's called existential generalization. Okay, so here is another example. Is this example is according to the biography of this Oxford mathematician Godfrey Hardy, who sponsored prodigy mathematician, Indian mathematician, his name Ramanujan, early in the 20th century. And according to the story, he was sick, and Godfrey visited him. Hardy visited him, and he noticed that the bed bears the number 1729. Hardy told him, "Oh, what a boring number," to which Ramanujan responded, no, it's very interesting. You can write it as the sum of 2 cube. And he demonstrated that this number can be written as 10 to the 3 plus 9 to the 3. Okay, which is mathematician, even when they are sick, they still think of some other number. Okay, but anyway, at any rate, so we can write that as okay, there is a number which is the sum of cube, and we can generalize it as we have done here, this example. Sometimes we can also build a proof that is considered to be non-constructive. What that means, we don't build it. In the previous example here, we rebuild that, we build that number. But sometimes we can argue, and this is really powerful, that there are some number that exist, but we don't need to show what it is. Either we don't know or we anticipate. And this is really exciting and very interesting case of proof. So let's look at some example here. Show that there exists irrational number x, irrational numbers x and y, such that when you put 1 to the power of the second, you get rational. Oh, this sounds interesting. So we know that the square root of 2 is irrational. Why? Because we could not find a and b where b is not equal to 0, and a and b are are integer. We could not write it as a ratio of 2 integer. So that's what it means. So we know that square root of 2 is irrational. We prove that. Okay, let's show that. Let's prove it. Okay, so we're gonna say, all right, let x equal square root of 2. Also, let y equal the square root of 2. Why? Because no one told us they shouldn't be the same. All right, so we can do that. Now, let's put x to the power of y, which is equal square root of 2 to the square root of 2. Okay, now what we think of this number? Okay, there are two possibilities. This is again with the nature of the real number. So this number, let's call it, for simplicity, let's call it big R. This R either what? Either rational or irrational. There is no other way. Now, if we say it is rational, then we're done. We just have two numbers that irrational, and we got a number that is what? Rational. If it is irrational, again, you can imagine somebody, some adversary, they say, no, we're not going to give you easy pass. No, this is irrational. Then say, no problem. So you say this is irrational, then I'm going to say, okay, x equal square root of 2 to the square root of 2. And then again, I'm going to let y equal the square root of 2. So I have two irrational numbers. I'm going to put one to the power of the other. So I'm going to say x the y. In this case, it's going to be equal to square root of 2 to the square root of 2 and all to the square root of 2. So this is the x, this is the y. Now, from our knowledge of powers, when we have something like this, 2 to the 2, and this one is to the 2, this is just mean 2, and let's make it different, 3. Then we're going to be multiply 2 to the 6. So we're going to do the same thing here. We're going to simplify. This will be square root of 2, and then we have the square root of 2 times square root of 2. But what this one mean? This mean square root of 2, this guy, 1 multiply square root of 2 times square root of 2, I just get 2. All right? And then square root of the square root of 2 is just 2. And we know 2 is rational. 2 is rational. So in either case, I just demonstrated that there exists a number, right? Two numbers that are irrational, and then out of these I can create a rational, which sometimes, you know, when we start, maybe it sounds not really clear. So from irrational, is it possible that I get rational? And this example really showed, all right, what is interesting here, without even having to know if this one really is irrational. Okay, because here is just if it is irrational, well, we already if it is rational, we already get one to be rational. If not, here there's no other way. So I find this one very intriguing. So we got some fact out of thin air, you can think about it, but it's not really. I mean, we did it, and there is the logic is really very tight. There is no way this is not the case. Well, one important skills that we need to learn is how to deny or show some universal statement to be false. Okay, so if somebody have a claim, a universal claim, and we can disprove it by just showing one example. Okay, and this is based on the ideas that if we have something of the form, okay, somebody there exists an x such that is not the case that b is same as, this is equivalent to it is not the case that for any x p of x. So what that means, if somebody give me something like this, all right, and then how I'm if I need to deny it, oh, it's just enough to find at least one counterexample, and then that's it. The whole theorem or claim or conjecture that's shown to be false. So look at some example. This is an example. Every positive integer, so notice that is every positive integer is the sum of a square of 3 integers. All right, so if we're going to put it in our beautiful predicate logic, we're going to write it something this format. For any x, if x is the positive integer, then there exists x and y and z and r in z plus what that mean anything other than the zeros and the negative, and we write a sum. So this is true. If you pick, if we choose x to be 14, then yes, we can choose x to be 3, so I have 3 times 3, y to be w to be 2 times 2, and r to be 1. Yeah, so in this case this is fine, but this one, it doesn't work for 7. 7, we know it is a prime number, all right? So we talk about prime number, so I can't write it any other way, right? So I can't write it as a sum of others. Okay, so this is a counterexample. So it's enough just to show one example. I don't have to do anything else, just only one example enough. Okay, so what that means is just in this case just enough to find just 7, and I say it's not the case, so this one failed. Some proof need to show uniqueness. So we know that by now, we know when you have something like this just means that there is at least, there are at least one. So it could be all, for all we know. All right, but sometimes I want to show there is one and only one. We use this symbol to indicate the uniqueness, but this is not really a symbol in a basic symbol in predicate logic. We can write that as in a way that express this uniqueness, but maybe we're gonna show that using Tarski's world. But let's not get distracted. So we want to show that there is x, there is one and only one x. So when you see something like that, okay, with the exclamation mark, this means there is one and only one. That's all. Uniqueness. That's what uniqueness means. Okay, so in order to prove something like that, I have to do two parts. I have to do two things. I have to show the existence, at least one, and then I have to show there's no other way, there's no other one other than one we just discovered. So we're going to show uniqueness. This way you show that something is unique. So let's look at some example. If A and B are real numbers, and A is not 0, then there is a unique real number R, such that A times R plus B is equal to 0. So what we can do, we can let R, we're going to say let R, or just make it, okay, let's say let R equal minus B over A. And we're going to take this one and going to substitute it here. So follow me here. So we're going to let it here, as I mentioned, and then we're going to substitute it here. So this is R. When we do this, what we get? We get minus B plus B is equal to 0. So what that means, this number we picked is become really a solution to this. So why this is a good show of existence? Because this is a real number. R is a real number. So when I divide a real number by a real number, and remember here A is not 0, then I'm gonna get back a real number. There's no way. This is a property what we call the closeness. So the real number are closed under division. Okay, provided the denominator is not 0. Okay, so here we just show there are some solution, and R is such that we find just one. Now the question is this the only one? And we're going to show next that is really the case. So it's like assuming that we have two. We have R, as we declared, and we have S, and see what happens. So here our S, okay, we assume there S, and then here's our R from before, okay. And then when we add both sides of the equation, what we get, and simplify, we get what we get. We cancel out. We get R equal to S. All right. So what that mean? It mean there is only one such solution, and here R and S just two names to the same thing. So we have covered quite a ground on proof. So when we are faced with some problem we want to prove, the best thing to start is to try the direct proof. So direct proof, here recall something of the form if P then Q. We assume P, and then we try to arrive at Q. If this is working well and good. If it doesn't work, then we will try the contrapositive, like we did a lot at this time. So we try this, it doesn't work, but we know that it has an equivalent. All right, we try that. And in this case, we're going to assume not Q, and then we're going to attempt to arrive at not P. If we do that, then we just succeeded. All right, sometimes a good idea is to use the axiom, that is the rule that we talked about, or some definition and so on. And we tried that different, try assuming P, arrive at Q, or maybe try not Q, then arrive at P. And sometimes we tried the backward reasoning. Remember in class, we did one example. We had a look at the sequence of of the premise, and then we try to have a clue where to start, and we backtrack. Okay, we say this is our end result. Let's say this is my end result. Then I'm gonna ask myself how I'm gonna get the P, and then maybe there is something else. What it led to be, and but what I need to have a way to get to the P. In this case, I need to use the modus bonus.